do an example to talk about circuit reduction and circuit solutions where we get to start to use some of the Thevenin-Norton kind of equivalences. And remember, one of the beautiful parts about a Thevenin-Norton equivalence is that I can take what is a voltage source and a resistor in series, and it becomes a current source and a resistor in parallel. And I can make this transformation back and forth, and these are really core things built around one-port models. So there's some incredible things that come out of these conversations. So figure out, let's take a look at a circuit like this, and you try to think to yourself, okay, this is going to get fun, but actually won't actually be too difficult here. The starting point right off the bat is to know that I have a resistive voltage divider in the front end, and that creates this voltage V1. Now, I'll know as a result that it's going to be RA over the sum of RA plus RV, and this V1 then would then be a nice voltage solution. And you think, great, is this completely unconnected to this circuit? And the answer is yes, it is. But this circuit over here directly has an impact of it because this term GM-V1 directly has an impact. And so as a result of solving that first stage, I actually have a circuit that looks something like what I've drawn down here. Okay, so now I've got the circuit reduced to this level, and now this source kind of looks like a dependent or independent source depending on how you look at it. This Vn is not in the rest of the circuit, so you could call it either way. Kind of depends on the way you want to think through it. The question is, okay, so now I need to solve it, and you go, okay, now I need to start doing some analysis. I have a node here, maybe I write KCL here, I write KCL at this node, and I grind through and I hope for the best. And that works, and that will be a perfectly good solution and may not take too long. And we get you the exact same answers we're gonna come to. But another way to do it would be to say, let me take a look at the Thevenin-Norton equivalent. So this is a current source and a resistor in parallel. That would be equivalent to these two elements in series. Likewise, the I2 and R2 elements give me these two, the R2 and the I2-R2 element in series. And this one, being that this is effectively not dependent on the rest of the circuit, it's pretty safe to say I can do this transformation as well. Dependent circuit sources are possible to be used in these transformations, but you must be careful of where its actual voltage or current that's controlling it comes from, and you do not lose it. You've got to be very, very careful. If you're careful with it, you can kind of make these things work. In this case, it's pretty straightforward. And so all of a sudden now I get a voltage source. By the way, notice there's a sign change here. The sign change occurs because the current was pointed downward. So it's R1 and the voltage source. But if I look at this circuit compared to this one, this feels a whole lot easier to deal with. Further, if I realize that I can swap these two elements, I get R1 and R2 in series, and then I get the two voltage sources together, and so I can simply add those results, which then gives me this wonderful circuit over here with these particular elements. As a result of that circuit, I can then quickly sort of solve this element by one of a couple different techniques, one of which is just finding the current and then plugging in terms of the output voltage there. I could do this, and I could also do this in terms of looking at superposition for those who are familiar with superposition techniques, and to realize that if I have one of the voltages off, this is just a voltage divider in one direction or a voltage divider in the other direction. And so I get a fairly nice and balanced structure here. Great. And then you say, well, what would this look like if I put in numbers? Well, of course, I have RA and RB are equal in this case, both at 1 kilo. R3 is at 4K, R1 and R2 are at 2K. That actually makes both of these two ratios be a half. So that kind of simplifies it. This whole GM R1 and RA plus RB gives me basically a number that's 2. So basically I get this nice expression here, which then simplifies so that V out is basically 4 volts minus the input voltage. And so what it shows is there's a way to kind of solve these circuits in a graphical way that isn't just necessarily just pushing through and plowing through equations. And sometimes that intuition really helps you solve it, and not just solve it, but also have confidence that you didn't make a mistake in the process.